what I would like to talk about first here is cascoded differential pairs. There's not going to be practically any analysis whatsoever because we know how cascoded things behave. So for the BJT case, that's going to look something like this. Here we have VCC. We're going to have a cascoded current source up here, where I'm just going to call this VB7 because this is transistor Q7. Here's Q5, so this will be VB5. Here's our node for Vout1. Then we get down to the NPN portion. This is going to be VB3 because this is Q3. Here is VN1, where this is Q1. And then we have the right-hand side of the circuit, which is just a mirror. Go out. So this is going to be Q8, Q6, Q4, Q2. And so what I'm going to do here is I'm just going to tie all of these bases together like so. Here's Vout2. Here's my tail current, IEE. And then here is VN2. Okay, so that's generally what it looks like. Is it symmetrical?
Yes.
All right, so what's our half circuit? A simple cascoded amplifier, right? So our half circuit looks like this. Since we know how the half circuit behaves, it is just so A V for our half circuit is GM1 times R up in parallel with R down, where this is R down and this is R up. So that means our differential mode gain A DM is, sorry, that should be a negative sign there, negative GM1 1 plus GM3 R01 in parallel with R pi 3 times R03 plus R01 in parallel with R pi 3. This is going to be in parallel, and because I'm writing too large, I'm going to have to put the thing that it's in parallel with on a separate line. One plus GM5 R naught 7 in parallel with R pi 5 times R naught 5 plus R naught 7 in parallel with R pi 5. Close that bracket. So this huge thing right here is just R down. This big thing right here is just R up. Okay. We covered those when we covered cascode amplifiers. All right. So don't really need to do, like I said, any derivation or anything here because we know exactly how this thing should behave because we know how the half circuit behaves. The MOSFET version is going to be extraordinarily similar, except that all of our R pi's are going to go to infinity. Okay. So do I need to explicitly draw out the MOSFET thing and all that crap?
But not the circuit, but probably the formula.
Okay. You guys tell me. All right, so this is the one for BJT, so I'm going to write BJT under it. All right, for the MOSFET version, we're going to have negative GM1 times 1 plus GM3 R naught 1 times R naught 3 plus R naught 1 sorry, I got that. No, I didn't. That whole thing. Parentheses, parentheses, close bracket, in parallel with 1 plus GM5 R naught 7 times R naught 5 plus R naught 7. Close, close. And that is for MOSFET. It is literally the exact same equation, except anytime we had anything in parallel with R pi, it was just that by itself. Okay. Differential, cascode differential pairs covered. They're now fair game for the test. Let me know when I can move to the next page so we can cover something new.
Is that the one before R7? Is that 4 or 5? Like the second to last, or not?
Yes.
Or not 5?
R naught 5 and then R naught 7.
And for both of these, it's negative GM1 multiplied by the total parallel combination.
That's correct.
Okay, I was just making sure I was looking at the brackets correctly.
Yes, yes, yes. Where's my phone? What was that alarm about? Mine didn't go off. Okay, well, I don't know. Somebody did. Okay. Maybe that was on Zoom. Okay, so cascoded differential pairs, both the BJT case and the MOSFET case have effectively been covered. So now let's move along to bigger and better things. Okay, so let's consider don't draw this. Let me talk our way through it first because I'm going to make several changes and you're just going to get annoyed with me. So if we have a simple differential pair amplifier like so, actually let's make it a MOSFET one just because I don't want to have to think about R pi. We have a MOSFET differential pair amplifier where this is transistor M1, this is transistor M2. Here is our tail current ISS. Here's VDD, VDD, RD, RD, V out 1, V out 2. Okay. VN1 and VN2. So if we were to try to make an integrated circuit differential pair, what would we do to get better headroom out of our circuit?
Use cascoded MOSFETs.
So cascoded is going to give us less headroom, but more output resistance.
Oh, so we use a resistor for our bias. Give us more headroom.
No. So a resistor also gives us less headroom because we're talking about the DC level of things, right?
Okay.
So we're just going to use PMOS current sources here to give us more headroom and a little bit more voltage gain. All right. So that's our first iteration here. We could replace these resistors RD with a BJT current source. So let's call this M3, and that's going to get in the way. Where these are tied together at the gates so that we can bias them with a single bias voltage. Let's just call it VB3 for the sake of argument. So will this change really change the small signal operation of our device at all? Not particularly, right? Because we have a PMOS current source up top where the source and the drain voltages are tied, excuse me, the gate and the source voltage are at the same AC potential. And so it's just going to look like R03 and R04 up there from everything that's connected at the bottom, okay? All right, so what I want to talk to you about today for this next bit is how we are going to take our double-ended input, double-ended output system and convert it into a double-ended input or differential input and a single-ended output, okay? Meaning that we only have one output voltage, all right? So the easiest way to do it, also kind of the dumbest way, is to just say, well, I only want to take into account V out 1, or I only want to take into account V out 2, and I just ignore the other output voltage. That gives me a single-ended output. What's the problem with that?
Your noise.
No. Our differential mode gain is predicated on the fact that we're looking at both. If we're only taking into account the gain of one half circuit, we only get half the gain, right? So if we consider VN1 to be 1/2 our differential input mode signal, and VN2 to be negative 1/2 our differential input mode signal, if we only look at one of these output quantities, our input signal is half as large. Therefore, our voltage gain will be half as large, okay? So that isn't a particularly good way to make our system a single-ended output. Instead, what we're going to do is we're going to put an active load on this system. So what I'm going to do here, I'm going to flip the direction of this transistor like so. And I'm going to kill V out 1 and tie it to this node. Effectively, what I've done here is instead of having current sources biasing this thing, I now have a current mirror biasing it. I now have a single-ended output. This particular configuration, I'm going to move the output voltage to the other side. Turns out to have the exact same gain as our differential output, except that we no longer have the negative sign to worry about. Okay, so this change from a PMOS current source to a PMOS current mirror gives us effectively the exact same characteristics as our differential pair amplifier, except that we no longer have an inverting amplifier because the voltage, the gain isn't inherently negative. This circuit is the single stage op-amp. So what we're going to spend the next several minutes doing is going through how this guy behaves and all that kind of good stuff, okay? Draw this now. Yes, thank you. I'll give you a minute to draw this. Yeah, so this is what we're going to be analyzing for the rest of the time we're in class today. We are going to be making some assumptions here. M1 and M2 are perfectly matched. M3 and M4 are matched, and channel length modulation can be ignored. All right, so the first thing that we are going to do is a large signal analysis. See how this guy behaves. Common mode input signals. So I'm going to say that VN1 is exactly equal to VN2 for this analysis. So, excuse me. If VN1 is equal to VN2, then that means VGS1 and VGS2 have to be equal, which in turn means M1 is carrying a current of 1/2 ISS, and M2 is carrying a current of 1/2 ISS. Excuse me. Are we okay with that? All right. So this current 1/2 ISS that is being drawn by transistor M1 is the reference current for our PMOS current mirror up here, right? So that means that we're drawing a current of 1/2 ISS through transistor M3, which I apparently erased my label for M3, so I'm going to go ahead and put that on here. We can observe Actually, I need to move that because it's going to get in the way of me drawing my VGSs. My apologies. So here's 1/2 ISS. Well, this current causes a voltage drop VSG3 to occur across M3. And obviously, the same voltage appears across the gate source terminals of transistor M4, which means transistor M4 is also carrying a current of 1/2 ISS. Excuse me. All right. So we know how all of our currents are flowing. So let's talk about what our output voltage DC term should be here. Okay. If these two transistors, M3 and M4, are carrying the same amount of current, they have to have the same gate source voltage, and they have to have the same drain source voltage. So from that, we can say that V out is simply VDD minus VSG3, okay? Because VSG3 is the same as VSD3, and they have to have the same drain source voltages in order to carry the same amount of current. So that's our DC operating point. V out is simply VDD minus VSG3, whatever that happens to be. All right. A couple of other things that we can notice here. If I had a load connected to my output terminal, what would the current flowing through that load be? I disagree. We have ISS going in, ISS going out. So our output current that this thing is going to source is going to be 0. Okay. So this is really what tells us that this device is not going to have a small signal, really. We're not going to see any common mode amplification, assuming that that current source ISS is a ideal current source. Sorry. So large signal analysis, this is our output voltage, and we should expect that our common mode output voltage, small signal, should be effectively 0 because we can't really push any current out. All right. Now we're going to get into the meat and potatoes of our small signal analysis, which is going to involve us drawing the small signal equivalent model for the circuit. All right, so there was our large signal analysis. We know how the output voltage behaves. We're kind of good to go there. Small signal analysis is similar, but not quite as easy. So I'm going to draw our small signal model. It's going to take a moment. It's rather large because there's 4 transistors that we need to account for, okay? So Here is R03. Here is GM3 VSG3. This is my source node for M3, and my source is grounded. Here is GM4 VSG4. Here's R04. This is the source for transistor 4. It is grounded, and because both of these sources are grounded, I can tie these two nodes together. All right. Here in the middle is going to be my gate node. I'm going to label it G34, like so. And then this voltage is then VSG3. And this voltage is VSG4. And my top transistors are taken care of. Here's where I'm going to put transistor M1. So here's GM1, VGS1. Here's R01. So this is the drain of transistor M1. Here is VGS1. Here's the gate of transistor 1. And we're going to have 1/2 VIDM here. Now over here, I'm going to draw transistor M2. GM2, VGS2. Plus minus VGS2. Negative 1/2 VIDM. Let's see, so this is drain 2, gate 2. This node right here is the source of 1. This node right here is the source of 2. And we know that our sources are tied together. And I'm going to call this node here in the middle the X. All right. So our last couple of connections here, we know that the drain of 3 is tied to the drain of 1. And we know that the gate of 3 is tied to the drain of 3. I'm going to call this voltage Vy. Excuse me. Similarly, we know that the drain of 4 is tied to the drain of 2. And we take our output voltage, V out, at that node. So this is our small signal model. It is a bit gnarly. Okay. So, first observation. This circuit isn't symmetrical. It's very, very close to being symmetrical, meaning if we had tied a short circuit between here to here, it would have perfect symmetry. Because it is very close to being symmetrical, we are going to say that this voltage here should be approximately ground. It's going to be pretty dang close, right? And that should make sense based on our current mirroring behavior that we observed earlier. For a common mode biasing signal, we have effectively identical currents flowing through both sides, so all of our voltages should be the same. So Vx should be pretty close to ground, an AC ground, okay? So we're going to talk our way through a few things here, all right? The first of which is that transistor M1 will have a small signal current, I1, flowing through it, where I1 is simply GM times 1/2 VIDM. We're simply using the transconductance of transistor M1 to explain how much current M1 carries due to corresponding input voltage, okay? Using that relationship, what should the current I2 be? Our input voltage is -1/2 VIDM, right? So if I drew a current down like this, going down in this direction, I2 would be -I1. If I draw it up, it's just the same thing as I1. Does that make sense? Okay. So I2 is GM times -1/2 VIDM, which is simply -I1. All right. Our current source for transistor M3. What's the voltage drop over? It's VSG3. So the current GM VSG3 and the voltage VSG3 are linearly related by a factor of 1/GM3. So effectively, because we have a diode connected transistor, we effectively just see R03 in parallel with 1/GM3 between node Vy and ground looking up. All right. Between Vy and ground looking down, we have a resistor R01. So R01, R03, and 1/GM3 are all in parallel. Right? From this, our voltage at node Vy is just the voltage drop over R01 in parallel with R03 in parallel with 1/GM3. Where the current flowing through it is just -I1. So our voltage Vy is -GM. Sorry, this should be 1, this should be 2, this should be 1. Sorry for not putting that. 1/2 VIDM times R01 in parallel with R03 in parallel with 1/GM3. R0 in parallel with R0 in parallel with 1 over GM3 is approximately just 1 over GM3 because this value is so much smaller than our channel length modulation resistances, typically speaking. So we can simplify this to be negative GM1 over GM3 times 1/2 VIDM. Are we okay with this thus far? Or at least you're gonna say you are.
I have a question.
Yes.
Why do we say that it's in our relationship for Vy? I think you said that the volt. Can you scroll down a bit so I can see the formula? I think my question lies there.
Okay.
So are we saying that negative GM1 multiplied by the 1/2 voltage is our total current?
Yes.
So
That's the total
that's equal
current
to I.
flowing into the negative polarity terminal of Vy. Yeah. So this equation right here is simply negative I1 times that parallel combination of resistances,
Okay.
which is giving us our voltage.
So I'm just hung up as to why we're only calculating with negative I1. I know it's Kirchhoff's voltage law, but isn't there a current flowing through R03 and R01?
The current flowing through, so R01, R03, and 1 over GM3 are all resistors in parallel. So I'm taking those 3 resistors in parallel, getting an equivalent resistance,
Right.
and then multiplying by the current flowing through that equivalent. So I don't have to take into account how it splits if I treat all of them as a single equivalent resistance.
Okay.
Does that make
Drop,
sense?
Yeah, voltage drop
Yeah.
in parallel is the same.
Yeah, so this is just Ohm's law.
Gotcha. Okay.
All right. Okay. Let's look at VSG4. VSG4 is just negative Vy. Are we okay with that? So a VSG4 is negative Vy. So that means that transistor I4 is carrying a current of negative GM4 Vy. Right? So VSG4 controls the amount of current source here, which for the sake of argument, we'll call it I4, which is, I believe, how I labeled it down here. Yeah. And that current I4 is simply GM4 times VSG4, where VSG4 is negative V1. Okay. So if we substitute in here, that's going to be GM4 times GM1 over GM3 times 1/2 EIDM. Since transistors 3 and 4 are perfectly matched, they must have the same transconductance. Meaning that GM3 and GM4 cancel each other, and we are left with GM1 times 1/2 VIDM, which is exactly a small signal current I1. All right, so what we're going to do now is we're going to calculate our output voltage. So let's look here and see exactly what's happening. The current flowing into this node is I4, which is the same as I1. And the current flowing out of this node is I2, which is negative I1. So we could just as easily say that there's a current of twice I1 flowing in. Okay. What's the resistance connected to this node? R04 in parallel with R02. Right? So from that, our output voltage, V out, is equal to I4 minus I2 times R02 in parallel with R04, which is GM4. Hold on, I'm messing this up. Excuse me, GM1 times 1/2 VIDM. That's my I4 term. Negative I2 is just plus GM2, but GM2 is the same as GM1 because transistors M1 and M2 are perfectly matched. So GM1, 1/2 VIDM multiplied by R02 in parallel with R04 is just VIDM times GM1 R02 in parallel with R54. And from this, our differential mode gain, or our I guess I'm going to call it a differential mode gain. So let me be explicit here. V out as a function of VIDM is GM1 R02 in parallel with R04. The exact same thing we would get with a current source loaded differential pair, except that we no longer have an inverting amplifier. Okay. All right. I have some more stuff here about if we were biasing it with a MOSFET current source as opposed to an ideal current source and what that would do to the headroom, but let's not worry about that. Let's call this our stopping point for this particular chart. I go through all that crap again in the integrated circuits class for those of you who want to suffer through it. All right, so this is the last bit of material that can show up on your test. Technically speaking, we could cascode this, we could do a couple of other things, but if I give you literally anything regarding the single stage op amp on your exam, it will be based on this very specific circuit where you don't have to do any analysis whatsoever. You know how it behaves. All right, so that's enough out of me for today. So I don't know, be safe. I don't know if the tornado warning is still in effect or anything like that. It looks sunny-ish outside. There are people walking about. Okay. Okay. All right. So, like I talked about at the beginning of class, your homework 2, I have added the answers, the numerical answers to that. We have changed the due date on that to Friday evening. Homework 3 has been posted. All of the numerical answers are available for that. It's due on Monday. The exam has been has been changed to Monday, and Friday is now going to be a review session. So come to class Friday with questions about things so that I can hopefully answer them.
Our take-home gets uploaded on Monday.
The take-home test, I'm trying to decide if I want to give you 1 design problem or 2 design problems. And that's why it hasn't been uploaded yet. No. If I give you 2 design problems, it'll be one's a BJT problem and one's a MOSFET problem, but I'm leaning towards just giving you a MOSFET problem because the math is less awful. So 1 MOSFET design problem and then some theory questions, and that'll be it.